All right, greetings, scholars. Beautiful mind here. So we're continuing our topic for week 6, but we have like an auxiliary section. The order's a little bit different, but this is the next logical flow. So we're moving to section 4.1 on linear functions. A few objectives here. In this section, you will represent a linear function, determine whether a linear function is increasing, decreasing, or constant, interpret slopes as a rate of change, write and interpret an equation for a linear function, graph linear functions, and determine whether lines are parallel or perpendicular, and then write the equation of a line parallel or perpendicular to a given line. Rapid growth. Picture planting a seedling and witnessing it shoot up in height in just a matter of days. While it might sound unbelievable, this phenomenon occurs with specific varieties of bamboo. Belonging to the grass family, these bamboo species hold the title for the world's fastest growing plants. In fact, there's a type of bamboo that can grow at a staggering rate of nearly 1.5 inches per hour. Within a day, it adds around 36 inches to its height, equivalent to an astonishing 3 feet. This consistent and rapid growth, like that of the bamboo plant, exemplifies a linear function. Okay. So a linear function is a function whose graph is a line. Linear functions can be written in the slope or intercept form of a line, which is f of x equals mx plus b. You might also hear me to refer to this as y equals mx plus b. That's like a classic. Where b is the initial or starting value of the function when x is 0, and m is the constant rate of change or the slope of the function. The y-intercept is at 0, b. So b serves as like a y-intercept, and the slope tells us our slope. Okay, so using a linear function to find the pressure on the diver. The pressure P in pounds per square inch on the diver in figure 4 depends upon her depth below the water surface, D in feet. The relationship may be modeled by this equation, and we're asked to restate this function in words. So let me see. The pressure as a function of depth is equal to 0.43 times the depth plus 14.696. I think that's all that they want, something like that. The image, she kind of looks like Michael Jackson. So let's see what the text says. The initial value there it is. Okay. So to restate the function in words, we need to describe each part of the equation. The pressure as a function of depth equals 434 thousandths times the depth plus 14 and 696 thousandths. That's fine. So the initial value of 14.696 is the pressure in pounds per square inch on the diver at a depth of 0 feet, which is the surface of the water. The rate of change or slope, which is the 0.434 pounds per square inch per foot. The rate of change is this, pounds per square, PSI per foot. This tells us that the pressure on the diver increases by 0.34 pounds per square inch for each foot her depth increases. So every time she goes down a foot, the pounds per square inch increases by 0.434. That's just a little bit of additional information. Okay. So determining whether a linear function is increasing, decreasing, or constant. So like if we have these images, like in a graphical sense, we say a function is increasing. As we trace it left to right, the graph goes up, so we say it's increasing. As we trace the graph from the left to the right and it goes down, we say the function is decreasing. And as we trace it from the left to the right, if it stays flat, we say that it's constant. Okay. So the slope determines if the function is an increasing linear function, a decreasing linear function, or a constant function. So when we have y equals mx plus b is an increasing function, that occurs if our slope is positive. We have y equals mx plus b as a decreasing function if our slope is negative, and y equals mx plus b is a constant function if our slope is 0. Okay. So deciding whether a function is increasing, increasing, decreasing, or constant. Studies from the early 2010s indicate that teens send about 60 texts a day, while more recent data indicates much higher messaging rates among all users, particularly considering the various apps with which people can communicate. For each of the following scenarios, find the linear equation that describes the relationship between the input value and the output value. Then determine whether the graph of the function is increasing, decreasing, or constant. Okay, so find a linear function that describes the relationship and then determine if it's increasing, decreasing, or constant. So for A, we have the total number of texts a teen sends is considered a function of time. So let me see, a function of time in days. So like the number that they send is based on however many days. The more the days, you would anticipate more text, right? The input is the number of days and the output is the total number of text sent. Let me see. So we can let T be the number of text sent and the D could be the days. So then we could have something like the number of text sent is a function of the day, something like that. And we would anticipate this to be an increasing function. Let me see. I feel like there's more we need. I'm going to kind of glance at this one just to see the format. The function can be represented as this. Now, where are they getting the 60 from? Oh, I see it. Studies in about 60 seconds. Okay. Okay, that's fine. Okay, I see what they're doing now. Okay. So, let me see. The teens send about 60 texts a day. So then our function will be what? 60 texts per day where X is considered each day. It is an increasing function. I think that's okay. Let's try part B. A person has a limit of 500 texts per month in their data plan. The input is the number of days and the output is the total number of texts remaining for the month. Okay, if they have a limit of 500 number of days, and I guess we're still using the 60 texts per day. So we could create a function like if we made a table of values, like on day 0, they still have 500. After 1 day, if they've done 60 texts, then it's going to be that result reduced by 500. Let me see if I want to do that. Okay, so I'm going to kind of work here. Again, the text kind of writes it as f of x equals mx plus b. I'm going to write it as y equals mx plus b. Okay. Now we said that like at the start of the plan, they have 500 texts, right? So when x is 0, the number of days is 0, the y-intercept is 500. So we know that b is 500 for that. Okay. After 1 day, if the person does 60 texts, so we're just trying to solve for the slope. So when x is 1, if they've done 60 texts, then they have what? 440 texts remaining. So then that means that if x is 1, our m we're trying to solve for, the y-intercept is 500. And again, we're saying after 1 day, they've used what, 60 texts. So then they have 440 texts remaining. So then from here, we get that the slope is going to be, what is that, negative 60? And I'll kind of keep working over here. So then if we have our slope and our y-intercept, then our function should take on the form for this one, negative 60x plus 500. Okay, let's choose a few test points to make sure this works. Okay. And this would be a decreasing function because it has a negative slope. Decreasing, right? That's my shorthand for decreasing. So at the start, like when they first start their plan, or if it's been 0 days, they haven't sent any text. So when x is 0, we get our desired 500. After 1 day, when x is 1, right? They've used the 60 texts for the day. So then they have, notice when we let x be 1, we get our desired result of 440. And then when x is 2, now we're subtracting 120. So this function is behaving the way that we would like it to. So I think we can be confident in this one. And again, this function has a negative slope, so we're going to go with that. Let's work on C. A person has a limited number of texts in their data plan for a cost of $50 per month. The input is the days and the output is the total cost of texting each month. Okay. So I'm going to start with y equals mx plus b again. Okay. The output is the cost. $50 per month, right? And if x is the number of days, let me see. The input is the number of days. The output is the cost for each month. I think that's a constant, right? They have unlimited text. So it's just going to be a flat fee for the month, right? So then that's going to take on the form f of x equals 50. Basically, it just means $50 per month. They can send as many texts as they want. All right? Like if they send 0 texts in a month, it still costs them $50. If they send 1 text per month, $50. 60 texts, $50. It doesn't matter how many texts they send, the cost is $50, right? So that makes sense. Okay. So we kind of stumbled on part A, but then once we got a sense of what they were looking for, then we were able to adjust. I didn't realize, anyway, we got to the bottom of it. Sorry, my table is so noisy. I keep trying. I guess I need to put some WD-40 on it or something so it can stop being so noisy. Okay. All right. So, and that's a constant function. That's a constant function. Okay. So I think the first one was increasing and then decreasing and then constant. Let's see. So, we kind of stumbled on this one, so we're going to kind of let that be. Right here, we got our negative 60x plus 500. The slope is negative, so it's a decreasing function. Okay. And then this was a constant function. The slope is 0, so it's constant. Okay. So I think we got those results. Let's go on to the next one. Our interpreting slope says rate of change. In the examples we've seen so far, the slope was provided to us. However, we often need to calculate the slope for a given input and output values. Recall that given two values, the input x1, x2, and the two corresponding output values, y1 and y2, which can be represented as a set of ordered pairs. The slope is the rise over the run. So the change in y over the change in x. Okay. Again, slope is, which is m, which is our rise over our run. The rise is our change in y. The run is our change in x. And like in a layman's term context, slope is like the steepness of a line. The higher the slope, the more steep the line is. The closer the slope is to 0, the more flat the line is. Okay. All right, here, so like for instance, we have a line and we're considering 2 points, so we want to find the slope. So the slope is going to be our change in our y, so like y2 minus y1 over our change in x, which is going to be like our x2 minus our x1, right? So the change in y over the change in x. Notice for this image, as we trace it from the left to the right, it's going up, so it should have a positive slope. Okay, let's try to work an example. Let me see, we got a Q&A here real quick. Are the units for slope always the units for the output over the units of the input? Yeah. All right. Slope is always like rise over run. That should be a yes. Yes, think of the units as the change of the output value for each unit and the change of the input value. An example of slope can be miles per hour or dollars per day. Notice that the units appear as a ratio of units of the output per units of the input. So the change in y over the change in x is essentially what they're saying. And again, we have the slope formula. So, as we kind of progress through the course, hopefully you've been like taking notes and you have like a notebook where you're being neat and organized. Within that notebook, it's a good idea to have like a formula sheet. So every time you come across like a relevant formula, you update your formula sheet. It's something that you can flip to, quickly and easily, have all of your formulas in one place ready to go. So this is the slope formula, which is the rise over the run. This little delta symbol here, that just means the change in y over the change in x. And then we express it like this. Okay. I'd rather just see this in action. So if f of x is a linear function and these two ordered pairs are points on the line, we're asked to find the slope, and then is this function increasing or decreasing? So if we want the slope, so again, one of my mentors would say, every time you use a formula, write it down. So since we're using a slope formula, that's going to be what? Y2 minus Y1 over X2 minus X1. And again, so that's going to be the slope. Also, because we're working with an ordered pair, I usually like to just automatically label them X1, Y1, X2, Y2. Okay. All right. And then, so then it makes applying them or using them much more easy, in my opinion. So then we're going to say Y2 minus Y1 over X2 minus X1. Notice I replace each component with a blank set of parentheses first. Then I plug my numbers in. And we do this because this helps us to keep track of our signs. Without those blank parentheses, it's really easy to lose track of the signs, and we increase our chances of making an error. Okay. Sorry, guys. Y2 is 1. Y1 is -2. Notice how the signs are playing it there. X2 is 8. And X1 is 3. Okay, so if we simplify this, on the top we have a double negative. So then that really is 1 plus 2 gives us a 3. And on bottom, 8 minus 3 is what? 5. So notice that this is positive, so that means our function is increasing. Okay. Find the slope, and then is the function increasing or decreasing? We got a positive slope of 3 over 5, so that means our function is increasing. Okay. We also write the slope as that the function is increasing because the slope is positive. As noted earlier, the order in which we write the points does not matter when we compute the slope of the line, as long as the first output value or y-coordinate used corresponds with the first input value, right? So we got to be consistent. If we do y2 first on top, we need to do x2 first on the bottom. If we do y1 first on top, we need to do x1 first on the bottom, right? We just need to be consistent in the way we order it, okay? Man, my battery. Here, let me turn on my low power mode. Battery is struggling. It's dropping fast. I was at 20, and it hadn't really been that long, and now it's already at 13%. I was like, oh man. And then if I try to charge it, it's this whole thing trying to charge while I'm doing the recording. So anyway, I'm gonna forge on. All right. So finding the population change from a linear function. The population of a city increased from 23,400 to 27,800 between 2008 and 2012. Find the change of population per year if we assume the change was constant from 2008 to 2012. So in other words, it's just asking us to find the slope between the 2 points, right? So again, every time we use a formula, write it down. Let me see. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And this is our slope. Now, we're given a set of ordered pairs. Let me kind of rearrange this a little bit. Let me see. It increased from there to there. Okay, so the 23,400 corresponds to the year 2008. And then the 27,800, that's not an 8. 27,800 corresponds to 2012. Okay, so those are the order pairs that were given. It wasn't written exclusively like that, but that's the implication. So we just wrote it out. Then I like to label them x1, y1, x2, y2, and then proceed. So if we're going to find the slope, y2 minus y1 over x2 minus x1. My y2 is 2012. My y1 is 2008. My x2 is the 27,800. My x1 is the 23,400. Okay. What is that? It looks like a 4. A 4 on top. Siri, what's 27,800 minus 23,400?
27,800 minus 23,400 is 4,000. 2,400.
Okay. So it looks like we get 1 over 1100. So whatever, let me think. Whatever that decimal is, that's how much the population is increasing per year. Did I get this backwards? I feel like I got it backwards. I feel like the year. I feel like I got it backwards. I feel like the year. I feel like this is backwards. Because the population should depend on the year, right? Whatever year it is, it tells us the population. I feel like I got these backwards. So let me switch these around real quick. Let me strike. I'll just switch them around. So I think this is supposed to be my Y value, like this. And then same thing over here. Okay. So then how that affects, basically this goes to the bottom and this goes to the top. That makes more sense, actually. Okay. So then that causes this to flip. And then that means that, because like I was like, the answer seems kind of weird. That was my red flag that I was like, wait a minute, I think I made a mistake. And then when I thought about it, I was like, oh, I think I got my X and Y's backwards, right? And so then, we made the necessary adjustments, and that's how it proceeds. Okay, so then this guy is really just this. So now what we're saying is that the population is increasing by 1,100 people per year. That makes more sense, right? Okay. Yeah, I think that's better. I feel better about that. Okay, so now let's look at the notes. Let's look at the prepared notes. People per year. Yeah. Yeah, again, my red flag was the final answer that I got. I got this like weird 1 over, and I was like, that looks like it's reversed. It was just a red flag. I was like, wait a minute, let me think about this again. And then I realized that I got my independent variable and my dependent variable backwards. So then I switched them and we straightened it out. So keep in mind, I don't really look at these before I do them. I usually do them like fresh. Like my first time seeing it is when I'm doing it live. And I do that intentionally because part of it is, with this whole experience, we do need to know how to catch mistakes and errors and how to find them and how to correct them. So that's actually part of it. So I try to do it as live and fresh without, with minimal preparation as possible. I should be able to get through these, doing that. So let's keep going. So I think we got this one. Okay. So here we're asked to write an equation for a linear function given a graph. Okay. All right. So we want an equation of this function. I'm going to pull from the graph. It looks like we have some, it crosses at a few points. It looks like the y-intercept is 2. So that ordered pair looks like it can be what? 0, 2. And another ordered pair, like I pulled this one. Let me choose a different color. This we can do like green. Something that pops a little bit more. And then another ordered pair that looks proper is like here. So that's the ordered pair 2, 8. Okay. If we want a linear function, we might use, again, I'm just a fan of starting at y equals mx plus b. You might see the book might call this f of x equals mx plus b. Okay. So I think we already have our y-intercept. It looks like our y-intercept is 2. So I'm just going to plug that in. That's going to go here. Then the slope, and then we can let's take the other ordered pair. Let me see. When x is 2, the corresponding y is 8. So then we don't know the slope. And the corresponding y is 8. So then now we can solve for the slope, or we could have used the slope formula, right? So let me finish this one, and then we'll confirm it with the slope formula as well. Subtract 2 on both sides. 6 equals 2m. Divide both sides by 2. Ultimately, we'll get m equals 3. So we got that the slope was 3. So then our function, and also you'll see me interchangeably use f of x. We can use that interchangeably with y. All right. So sometimes I'll write it as y, but I think that the text is going to write it as f of x. So that's the only reason I switched it. Our slope was 3x and our y was 2. So our claim is that this is the equation of the function. When x is 0, we get 2. When x is 2, we get 8. Another point, when x is negative 2, that's a negative 6, so we get negative 4. It looks like it's working out, right? And if we wanted to showcase the slope formula, I'm being lazy. Okay, stop being lazy. x1, y1, x2, y2, right? So then the slope formula, y2 minus y1 over x2 minus x1. Okay. So then that would be what? 2 minus 8. Oh my goodness, man. She is reading fast. 2 minus 8. I gotta be careful. I gotta be careful. We're not even halfway. We got a ways to go. I might need to go get my charger. Oh, I need to find that adapter. Okay, so we said 2 minus 8 divided by 0 minus 2. That's going to be a negative 6 over negative 2, which is a positive 3. All right, so we got the same slope, okay? So we saw 2 different ways to find the slope. Once we had the slope and the y-intercept, we just plugged those into our slope-intercept formula, okay? So then our function was 3x plus 2. Okay, I think this is good. Oh, and they did leave it as y equals. And they used the point slope form. So they did, there's a little bit different, but that's okay. So we could have left it as y equals, and that's fine. Okay. And I think, this is, just a little bit more analysis there. Okay. So writing an equation for a linear cost function, suppose Ben starts a company in which he incurs a fixed cost of $12.50 per month for the overhead, which includes his office rent. His production costs are $37.50 per item. Write a linear function C, where C of x is the cost for x items produced in a given month. Okay. So it sounds like there's a fixed cost plus a variable cost, right? So his cost function, let me see. His fixed cost is the $12.50 per month, which includes his rent. So we could say the $12.50 plus his variable cost is $37.50 per item. So 37.5 times each item produced. So something like this. This is a linear function. All right. Okay. And it might be reversed, but yeah, that's good. Oh, did I forget something? Yeah, I think we're good. So we got the exact same thing. Okay. Okay. So writing an equation for a linear function given 2 points. If f is a linear function with these 2 pieces of information given, find an equation for the function and slope-intercept. So it's basically saying f of 3 equals negative 2 and f of 8 equals 1. So those are 2 ordered pairs, right? So the first piece of information is saying that when x is 3, the corresponding y is negative 2. And when x is 8, the corresponding y is 1. Right? So we can label these x1, y1, x2, y2. And there are more other ways to find these equations. I'm just doing the way that I'm most comfortable with. And it wants the final result here in slope-intercept form. That's like the y equals mx plus b. So I'm actually just going to start with y equals mx plus b. The book might start with the point slope formula, which is y minus y1 equals m times x minus x1. Then they plug in the x1 and y1 is the same x1 and y1 that you see in purple. And then, you can use that we typically use that one when we have a point and a slope. But I feel like doing it the way that I'm doing is more simple. Okay. Well, okay. So in this case, we don't have our y-intercept, so we can go ahead and find the slope. So if we were going to use our slope formula, let me see. So that's going to be our y2 minus y1 over x2 minus x1. Again, that's our slope. So our y2 is 1, our y1 is negative 2, our x2 is 8, x1 is 3. That's a 3 over 5, okay? So that's our slope. And we don't know the y-intercept, but we do have these other points. So I'm going to plug in, I'm just going to plug in the second point because it doesn't have the negatives, right? So we just found the slope was this. If I'm using the second point, my x is 8. We don't know the y-intercept, so I'm going to leave it. And the corresponding y is 1. Okay. So then ultimately we get b equals 1 minus 24 over 5, right? To multiply fractions, we multiply the top with the top, bottom with the bottom. 8 times 3 is 24. We subtract, we get this. And that's going to be equal to negative 19 over 5. Okay, so we got our y-intercept and we have our slope. So then we put those two pieces of information together. Y equals 3 over 5x minus 19 over 5. So my tablet is holding strong at 10%. I felt like I shouldn't have said anything because I feel like now in a few minutes it's going to drop, but it's been holding strong at 10%. Okay. And then we can check, oh, it's f of x. So we definitely need to put this one in f of x because that's how the question started. Okay. So when x is 3, 9 over 5 minus 19 over 5 is a negative 10 over 5, which is negative 2. That one checks out. And then when x is 8, 8 times 3 is 24. So 24 minus 19 is what? 5 over 5, which is 1. Okay. So this linear function satisfies the two given points. Okay. And here's a type version. So they converted the given points to ordered pairs. They found a slope. They got the same slope that we got. You can see it here if you zoom in. Now they use the point slope. So, you know, y minus y1 equals m times x minus x1. That's called the point slope form of an equation of a line. We typically use that when we're given a point and a slope. We found the slope and we used one of our given points. And then we solve for y and they got the same thing that we got. Okay. Let's keep going. That's 4 drawn. We're not even halfway. We got a ways to go. This is a long section, by the way. Let's keep going. So modeling real-world problems with linear functions. In the real world, problems are not always explicitly stated in terms of a function or represented with a graph. Fortunately, we can analyze the problem by first representing it as a linear function and then interpreting the components of the function. As long as we know or can figure out the initial value of the rate of change of a linear function, we can solve many different kinds of real-world problems. So given a linear function and the initial value and the rate of change of the function, we can evaluate f of c, determine the initial value and the rate of change or the slope, substitute these into y equals mx plus b, and then evaluate the function at x equals c. Let's just see this in action. All right, so Marcus currently has 200 songs in his music collection. Every month he adds 15 new songs. Write a formula for the number of songs in his collection as a function of time, the number of months. How many songs will he own at the end of the year? Okay. So we have the number of songs as a function of the months, the time, okay? A linear function. So we're working with, I'm going to start with y equals mx plus b, right? Now we want the number of songs as a function of his month. Okay, so it says so when we started this analysis, it says he's starting with 200 songs. So that's like a wire intercept. Okay. So that's essentially telling us that the B is 200 songs. And then every month he adds 15 new songs. So we can capture that as follows. So let me see. The number of songs based on the time and months is going to be 15 songs for each month plus the 200 that he started with. All right. So like, for instance, when we say T is 0, when we start, he starts with 200 songs. Then after 1 month, he's going to add 15 songs. So when we let T be 1, he'll have his 215. After 2 months, now he's going to add 30 songs. So now we'll be at 230, so on and so on and so on. All right. Okay. I feel like this is good. How many songs? Let me see. So write a formula for the number of songs in this collection as a function of time, the number of months, and then how many songs we have at the end of the year. So then after 12 months, if we let T be 12, so this is our function that we got. And then the number of songs after 12 months is going to be 15 times 12 plus 200. Okay. 10 times that is what? 150 plus 30 is 180. So then 380 songs. Okay, so that's what we got when we did it. Let's see. Okay, so it looks like they did something similar. So if we have our y equals mx plus b, he's starting with 200 songs and they grow by 15 songs every month. So that's our slope. I think we got the same function and they got the 380. Like we got after 12 months, we got the same thing. Okay, not too bad. Almost halfway. I'm telling you, this one is a long one. So that's part of the reason why I'm kind of going a little bit fast. I've actually been working on this like a good portion of the day. And then as soon as I finished work on it, I took like maybe a 10-minute break and I'm trying to just pump out this video. This is the last video we need for week 6. So that's why I'm just trying to get it done so I can clear my mind. And then hopefully I can get ahead. All right. Go ahead and do the stuff for next week. And then maybe the week after that, maybe. It just depends on how I feel. So with example 9, using a linear function to calculate salary based on commission. Working as an insurance salesperson, Aya, I don't even know. Ilya? I have no idea. Earns a base salary plus a commission on each new policy. Therefore, Ilya's weekly income, I, depends on the number of new policies he sells. I thought it was a she. He sells during the week. Last week, he sold 3 new policies and earned $760 for the week. The week before, he sold 5 new policies and earned this. Find an equation I of n and interpret the meaning of the component. Okay, let me see. Therefore, weekly income depends on he sells. Last week, he sold. Okay. So they gave us, and it says using linear functions. So I think it's a safe assumption here that it's linear in nature. Let me see. Last week, let me see. He sold 3 policies. Okay, let me see. Find an equation let me see. His income based on the number of policies. So we're writing a function to describe his income based on his weekly income based on the policies sold. So 1 week he did 3 policies and his income was $760 for the week. Okay. Another week, he sold 5 policies and he earned $920 for the week. Okay. $1,000 a week. I mean, that's okay. That's not too bad. It just depends on how difficult it is for him. If I were him, I would be trying to sell at least 6 per week. If he can double that, then that would be about $2,000 a week. That's like 8. That's a good chunk of change. $8,000 a month. Let's go. Right. Anyway. Okay. So these are our order pairs, right? So we're gonna basically find a linear function that passes through these 2 points, right? So I like to label these. We should do I and N, but I can see it better if I do it in terms of X and Y. Let me think. I mean, okay, so it would be, this would be N1 and then what? I1 and then N2 and I2. And so then our slope, y sub 2, so it would be what? I2 minus I1 over N2 minus N1, okay? That's like our y2 minus y1 over x2 minus x1, okay? Okay, so our I2, we got 920 minus 760 over 5 minus 3. If that were 800, that would be what? 120 plus 40. It looks like it's a 160 over 2, which is 80. That's the slope. Okay. So if we're doing y equals mx plus b, that's just my default, and I'll plug in what we need as needed. Let me see. So my I as a function of n is going to be the slope, which is 80 times n. Oh, we still don't know b. So we need to go and find the y-intercept. Okay. So what I'm going to do, I'm going to plug in one of the points. We plugged in a slope, right? So I'm just going to choose the second one. It just looks like it's a little bit easier. So when n is 5, we don't know the y-intercept, but the corresponding y value is 920, okay? 40, so what is that, 400? So then subtract 400, looks like it's 520. Let's see. So maybe his base salary is 520, something like that. That might be the case, yeah. Like if he doesn't sell any policies, one, he might not be at the company too much longer if he's not selling policies and just collecting a check, because this is capitalism. So, you know, but it sounds like if he doesn't sell any policies, he'll earn 520. Okay. So then let's put all this together. So his income based on policies sold, his slope is going to be 80 times each policy plus is 520. Okay. So we need to make sure that this works. Did you all enjoy the halftime? I didn't watch any of the Super Bowls. I didn't watch the halftime show or anything. I don't know. I was just in my own world. I'm so removed. Like, I don't know. I just don't care. I mean, when I was younger, we used to go to like Super Bowl parties, but I guess everything is so different now. Those used to be really fun. It was just a bunch of people that, you know, we knew or we got to know. It was just fun. Just, you know, and like I remember enjoying the commercials and the halftime. I didn't really care about the game, but I did enjoy the halftime shows. And back in the day, the commercials, like they would go all out for the commercials and they were fun, like witty and, you know, things of that nature. But I don't know, for whatever reason, I just don't care today, like in this day and age. But anywho, okay, let's see if this makes sense. All right. If we let n be 3, that's 240. That's a 60, 760 is correct. If we let n be 5, it's 400, 920. Okay. So we have a linear function that passes through these 2 points. So this should be his income based on number of policies sold in a week. And it looks like if he sells 0 policies in a week, they'll give him $500 for the week. But again, I don't think that company will want to keep him around too long if he's not selling policies, right? So yeah, man. Okay, let's forward on. So 80N plus 520. I think that's exactly what we got. Yeah. Okay. Okay. So it's example 10. Using tabular form to write an equation for a linear function. Use the table to write a linear equation. So we want the equation of the line that describes this table. So since it's linear, we can use, again, I'm just going to start with y equals mx plus b. So we have the value when x is 0. So they give us our y-intercept, our b. The b is 1,000. Okay. So then we're going to use a second point to solve for the slope. So again, when x is 2, we don't know the slope. The y-intercept is 1,000, and the corresponding y is 1080. So then if we solve for m, it looks like m is 40. Okay. So we got our b, we got our slope. So then I'll kind of work over here. We can write this as y equals 40x plus 1,000. But then let me put it in context of there. So then P of W is going to be what? 40W plus 1,000. All right. So that's another way that we can do this. I just did it in terms of X and Y first, and then put it in the right units at the end. So for instance, when W is 0, we get 1,000. When W is 2, we get 1080. When W is 4, 1160. When W is 6, 1240, right? It checks out. Use the table to, yeah, that's it. So we want this guy here. Man, okay. Let's keep going. We're looking pretty good. Copy. Whew. Okay, where'd it go? Solution. Okay, so I think they got the same thing. Sorry, doing a little bit of doing a little bit of stretching. I was scratching like literally the center of my back. I'm usually not flexible, but I was able to reach the center of my back here today. So I don't know. It feels like things are always changing. I just keep trying and just adjust. Okay. So I think we're good. All right, let's keep going. So I think they got the same thing that we got. Is the initial value always provided in the table like as in table 1? Was that table 1? All right. Is the initial value always provided? Take a moment. Boo 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 boo. Jeopardy, right? Okay, that result should be no, right? It's not always provided. Sometimes the initial value is provided in the table of values, but sometimes it is not. If you see an input of 0, then the initial value will be the corresponding output. If the initial value was not provided because there is no value of the input on the table equal to 0, find the slope, substitute in one coordinate of pairs, right, and solve for b. Okay. And that's what we've been doing, but I like that they asked that question, so that's why I included it. So we're asked to graph this by plotting points. Okay, I'm going to do a rough sketch for this one. So notice that this is in the form y equals mx plus b. So that's telling us that our y-intercept is 5 and it has a negative slope, right? So I'm just going to do a rough sketch, just because. Now, if I wanted to be more precise, I would use graph paper. Okay. So my positive x is in this direction. Positive y is in this direction. My y-intercept is 5, and we have a slope of -2/3. Okay. So let me see. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. And so I did my best to try to make these spacings uniform. If they're skewed, then it would throw off our image. But again, I'm just doing a rough sketch. 15/2, 7.5. 1, 2, 3. So kind of over there. Okay, that's fine. Okay, so our y-intercept is 5. Here, let me label this. We got our origin. This was 1, 2, 3. Okay. And so because our b is 5, so we'll put a point here. I was doing a quick calculation to calculate the x-intercept. I got like 7.5, so that will put an x-intercept over here. We can use our slope of -2/3. So if we go down 2 and over 3, we get a point about here, and then we connect them with the straight edge. I use the x-intercept as just an additional point to kind of, for precision or whatever. And so it's close enough. Okay. Notice I extended my line across the entire graph. And we really should use arrows on the end to signify that it goes on forever. It continues to pattern in either direction forever. Okay. And again, like the points are a little bit off because I did a rough sketch, right? If I wanted to minimize those kind of errors, I would use graph paper, right? So what we did, graphing a line is easiest in my opinion, if we use the slope-intercept form, y equals mx plus b. Once we know the b, that's our y-intercept, that tells us the first point, and then we use the slope to get the second point, and then we connect those 2 points with the straight edge. And that's essentially what I did here. The slope in this case was a -2/3, so that means we went down by 2 and then to the right by 3, and we plotted a second point, and we got this image. Okay, let's keep going. So I think what they did, they made a table of values. So they chose several values of x, found the corresponding y's, plotted them on a graph, and connected them with the straight edge. It's essentially the same technique, right? It's articulated different ways, but we got the same thing. So you use whichever you resonate more with. Man, okay, we are officially at the halfway mark for this section. Like, this is a long section. We finally got to the halfway mark. I kept trying not to say anything because I felt like that would draw it out. But let's forge on. So the graphical interpretation of a linear function. In the equation f of x equals mx plus b, b is the y-intercept of the graph, which is how you see me been using it so far. And m is the slope, right? And again, slope is the rise over the run, the change in y over the change in x. And we've been using this formula also as well. Do all linear functions have y-intercepts? Yes, right? That should be a yes. Let's see. Take a moment to yourself. Don't take my word for it. Sometimes I get these wrong. So I'm thinking it's yes, but I want you to take a moment for yourself to think. What do you think? Is it yes or is it no? Do 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 do. Boom, ba-dum, boom, 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 boom. Okay, that was a moment, right? So let's see. Yes, all linear functions cross the y-axis and therefore have y-intercepts. Note, a vertical line is parallel to the y-axis, does not have a y-intercept, but is also not a function, right? So we were specifically talking about linear functions. Okay. So given the equation for a linear function, graph the linear function. And so this is basically what I did in the previous example. Once we have the slope-intercept form, y equals mx plus b, our b, which is our y-intercept, tells us, that's usually where we like to start on the y-axis. And then we use the slope to generate a second point. We connect those 2 points with a straight edge, and that's our graph. Okay. So this is kind of a repeat. I think we actually just did this one. I guess they wanted us to do it a different way in the previous example. Let me make sure I don't have repeat things here. Yeah, I don't know why. I guess, I think they wanted us to do it a different way. Like the way they did this one earlier, they chose several values of x and found the corresponding y's and plotted the points. Now they're doing it the way that I did it, where we started the y-intercept and then used the slope. So I'm just going to use my prepared notes because we've done it that way already. And we got something like this. Okay. All right. So then we want to introduce this concept on transformations of graphs, right? I want to say in the previous example, we introduced the parent functions or the base functions. I think what do they call them? I forget how the textbook refers to them, but I know at that moment I was like, you'll hear me refer to these as base functions or parent functions. So now what we want to do is take those parent functions and start applying transformations on them to graph them. And so these first couple of transformations we have here are vertical stretching or compressing. All right. And I'm just going to summarize this. So given a function, if we multiply the outside of the base function by a number larger than 1, it's going to cause a vertical stretch. And it follows our intuition. If we multiply the outside of our base function by a number between 0 and 1, it's going to cause a vertical shrink. So outside manipulations cause a vertical change, and they follow our intuition, right? A number is larger than 1, so it gets bigger. A number between 0 and 1, or a number smaller than 1, so it gets smaller, right? So if outside manipulations cause vertical changes and they follow our intuition, so then maybe we can describe, inside manipulations. Let me see. There's a couple of things going on here. Let me see. So like, for instance, here, in these two cases, they multiplied the outside by a number larger than 1, so it caused a vertical stretch. The purple is just like the original, the identity function, okay? With these two examples, they multiplied by numbers between 0 and 1, so it caused a vertical shrink. So it got smushed vertically, closer to the x-axis. And then in this case, if we take those compressed ones, if we multiply the outside by a negative, that's like the y's go from positive to negative, so it flips vertically. So this causes it to flip top to bottom. Yeah, same thing here. The purple flips top to bottom. All of these guys get flipped top to bottom, right? So if we multiply the outside by a negative, it flips our image vertically, okay? So in this equation, f of x equals mx, where m is acting as the vertical stretch or compression of the identity function. When m is negative, wait a minute, something's missing. Okay. I could edit it here. Yeah, it does look like something is missing. Okay, I think it's okay for now, yeah. So m is acting as a vertical stretch or compression of the identity function. When m is negative, there's also a vertical reflection. It flips it vertically. I don't really like how this one is putting... This is actually 1, 2... These are 3 different transformations that it's trying to put into like one articulation. And I'll try to list them out right now. So given our function, our parent function, if we multiply the outside of the parent function by a number larger than 1, it causes a vertical stretch. If we multiply the outside by a number between 0 and 1, it causes a vertical shrink or compression. If we multiply the outside of our parent function by a negative, it flips it vertically, right? So again, outside manipulations cause a vertical change and they follow our intuition. That summarizes the manipulations going on here, okay? So these were all outside manipulations. Let's see the next one. Okay, and those were all multiplications. So now these are still, so we're still missing some because I don't remember doing the other part of it. But these are still outside manipulations, but instead of multiplying, we're adding and subtracting numbers, right? If we add a positive on the outside, it causes our entire graph to go up by that many units. If we subtract a positive on the outside, it causes the entire graph to go down by that many units, right? So again, these are all outside manipulations causing vertical changes, okay? I'm going to kind of let that be for now. So given the equation of a linear function, use transformations to graph a linear function in the form of y equals mx plus b. So first we graph the identity function, then we stretch it vertically or compress it by the graph by factoring m, and then shift it up or down b units. Okay, let's see it in action. So graph this using transformations. Okay, I'll do a rough sketch. So say this is our positive x in this direction. And it's our positive y in this direction. Okay. Let me see. So first we're going to start with the identity function y equals x. that's not gonna snap. Okay, and this is just y equals x. Let me see. So we multiply the identity function by a half. Notice that 1/2 is between 0 and 1. So that's going to cause a vertical shrink by a factor of 2. So the y values basically get cut in half. The x values stay the same, but it smushes it vertically. And then we subtracted a 3 on the outside, so that causes the entire graph to shift down by 3, right? So let me see. So something like this. That's about right. So basically the x value stayed the same, but the y values got cut in half. Then because of that -3, the entire graph shifts down by 3 units. All right. So something like this. All right, wherever the 3 is. We just shifted it down by 3. So then this is going to be our f of x, 1/2 x minus 3. All right. Okay. So something like that. So let's see how the textbook did it. So first they multiplied by a half, right? So it's like the y values all got cut in half. So that's where the blue comes from. Then they shifted, from there, they shifted the entire thing down by 3 units and they get this final result, all right? Okay, so that's similar to what we have. Let's try some more. Okay, match each equation to the linear function with one of its lines. So for part A, we have y equals, or f equals 2x plus 3. So that means our y-intercept is 3 and it has a positive slope of 2. So that means we go up 2 and over 1. So it looks like f is 1, or the red. Okay. That's because the y-intercept is 3 and it has a slope of positive 2, which means we go up 2 and over 1. Okay. G has a y-intercept of -3. I think there's only one that has a y-intercept of -3. So that looks like it's number 3, which is, I don't even think I have that color. I guess I'll use this one, green. It's close enough. So it looks like that's line number 3. C, the y-intercept is 3, and then it has a slope of -2. So I think there's only one graph that has a y-intercept of 3 with a negative slope, and that's graph number 4. It's close to black, so I'll use black. It's really navy blue, but you know, I don't want to mess with my colors. And then a y-intercept of 3 and a slope of 1/2. So we go up 1 and over 2, and that's equation 2. Okay, so 1, 3, 4, 2. Okay, right here. You see the 1 there, 3, 4, and 2. Okay. Okay, forging ahead, forging on, trying to keep a steady rhythm or pace. Just we're almost there. We're not too far. We're much closer than we've been all day, so we're just gonna keep going. All right, and this is just more of that same one. Okay, I think we're okay with those. Do all linear functions have x-intercepts? Take a moment to think about that for yourself. Boom, ba-dum, boom, 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 boom. Alex. So now I'm getting this image of like it was a Saturday Night Live skit where one of the comedians was pretending to be Sean Connery. He was like, he was just going in on Alex, taunting him. It was hilarious at the time. I think it's inappropriate for now, so I'm not going to repeat his jokes, but you're welcome to like look those up and find that skit. I don't know if it's still funny in this day and age. I know things are different, but I just remember laughing at it. Alex, yes. It's just so silly. It was hilarious. Just check it out. Okay, so do all linear functions have x-intercepts? I would say no, because like if you have a horizontal line, it has a y-intercept but no x-intercept, right? So you're not, and that's a linear function, so it should be no. No, however, linear functions of the form y equals c, where c is a non-zero real number, are the only examples of linear functions with no x-intercept. So for example, when y equals 5, that's going to be a horizontal line 5 units above the x-axis, and it has no x-intercept. Okay, so constant functions. Okay, we're not too bad. Let's keep going. So the x-intercept of a function is a value when our y is equal to 0. It can be solved by setting our equation equal to 0. Okay, if we want to find the x-intercept. So to find the x-intercept, we set y to 0 and solve. Okay. So then if we set y to 0, we're going to have 1/2 x minus 3 equals 0. Okay. Add 3 on both sides. And then we can multiply by 2. So the x-intercept is 6. And we should capture it as 6, 0. Okay. Okay, let's go with that. Okay. So then horizontal and vertical lines. Lines can be horizontal or vertical. A horizontal line is a line defined as y equals some number. A vertical line is going to be defined as x equals some number. Okay. Keep in mind that a vertical line is not a function, but we can still talk about vertical lines. Okay. So write the equation of the line graphed. So notice here, no matter, we have a horizontal line. So no matter, oh no. What? Darn, I guess I missed that one. Oh, I got the order backwards. Okay. I kind of want to change that, but I can change it here. I don't know how that happened. Okay. So write the equation of the line graphed here. What slide am I on? 63. And my device is kind of throwing a tantrum a bit. I think we're okay. So if we have a flat horizontal line, no matter what x value we choose, y is always -4 in this case. So then we could say something like f of x equals -4. You're not going to paste for me? Okay, that's okay. It's been a long day. We're almost done. Copy. Okay. Right, and so, yeah, we put f of x equals -4, or this is the same as y equals -4. Oh, I see what happened. I just forgot to delete it. Okay, let me just remove this now. I see what's going on. Let me get rid of this. Delete. So again, for any value of x, the value of y is -4. That's fine. I just forgot to delete it. Okay, so then for this one. So this one, we have a vertical line. We can also choose the values of y and find the corresponding x. No matter what value of y we choose, x is always 7 in this case. So the equation of this line is going to be x equals 7. Okay. We're almost there, and it's going pretty quick. So we say that two lines are parallel if they do not intersect. The slopes of the lines are the same. So lines that are parallel typically have the same slope with different y-intercepts. Okay. And then we say that two lines are perpendicular if the product of the slopes is -1, or in other words, if one slope is the negative reciprocal of the other. All right. So you can find it two different ways. Let me say that one more time. So we say that two lines are perpendicular. Perpendicular means that the lines, when they cross, they make a 90-degree angle. This occurs when the product of their slope is -1, or you can say when one slope is the negative reciprocal of the other. Okay, so you can use whichever one of those that you resonate with. So given the functions below, identify the function whose graphs are a pair of parallel lines and a pair of perpendicular lines. Let me see. So given these functions, which ones are parallel and which are perpendicular? Okay. Let me see. So for instance, the slope of f is 2. Okay. The slope of j is also 2. So they have the same slope with different y-intercepts. So f should be parallel. It looks like the function f is parallel to function j. And then it looks like that implies that the function g is perpendicular to function h. Notice that the slope of g is 1/2, and the negative reciprocal of 1/2 is -2. If we took the slope from g and we multiplied it by the slope from h, we get a result of -1, right? These are the shorthands for parallel and perpendicular. Okay, so we're saying that f is parallel to j and g is perpendicular to h. Okay. All right, we are moving and grooving, holding strong, almost there. Got a lot going on here. Let me see. Parallel, let me see. F and J each have, so they represent parallel lines. Perpendicular lines have negative reciprocal slopes. So that's G and H. So what we said is correct. And then we have an image here just to kind of like drive it home. You can see F and J parallel to each other, and then H and G perpendicular. That probably would have been better if they put those on separate graphs, because that's kind of jumbled looking like that. But you know, that's just how it unfolded. I'm going to just kind of let this be. Here we're asked to find a line parallel to this line that passes through this point. Okay. So if we want our line to be parallel, it needs to have the same slope. So it's already in the form of y equals mx plus b. So then the slope, our desired slope, is going to be 3. It's going to have this slope, and it's going to pass through the point 3, 0. All right. So if we want the equation of a line with this slope passing through this point, then we can use y equals mx plus b. Okay, let's plug in what we have. So our slope is 3. Let me see, when we're also given that x is 3. We don't know the y-intercept, and the corresponding y is 0. Okay, so if we solve for b from here, b equals -9. Okay, so then our function is going to be what? 3x minus 9. So this is a function that has a slope of 3, so that means it's parallel. And we need to confirm that the order pair 3, 0 is on this line. So when x is 3, 9 minus 9 is indeed 0. It checks out. All right. So then this should be it. You can see it here. Okay. And then here's an image, a pictorial representation of those two graphed together. All right, less than 10 slides to go. A horizontal line has a slope of 0 and a vertical line has an undefined slope. These two lines are perpendicular, but the product of the slope is not 1. Doesn't this fact contradict the definition of perpendicular lines, right? We said earlier that perpendicular lines, the product of their slope is -1, but how come when you take the product of the slope from a horizontal line with the slope of let me see. When we have a horizontal line and a perpendicular line, when we have a horizontal line with a vertical line, they are perpendicular, but the product of their slope is not -1. Why is this the case, right? Because, take a moment. Right? Because vertical lines are not functions. All right. So that pertains to that statement that we made earlier pertains to functions. the product of two non-vertical lines, there with the slope being -1, right? It's just because the vertical line is not a function. So let me see. For two perpendicular functions, the product of their slope is -1. However, a vertical line is not a function, so the definition is not contradicted. I'm going to just kind of let this be and go into the next part. Find the equation of a line perpendicular to this that passes through this point. Okay. So if their slope is 3 and we want our line to be perpendicular, then our slope needs to be the negative reciprocal of 3. Okay. So then our desired slope, the negative reciprocal of 3 is going to be a -1/3. We wanted to pass to the point 3, 0. Okay. I'm just a fan of starting at y equals mx plus b. Let's plug in what we have. Our slope is a -1/3. We're given that x is 3. We're solving for b, and we're given that y is 0. So then ultimately we get that b equals 1. So then our function is going to take on the form -1/3x plus 1. Okay. So notice that when x is 3, we get our 0. It has a slope of a negative reciprocal. So I think we're good there. Okay, we're in the home stretch. We're almost there. A few slides left. Okay, I'm going to let that be. I think this is the official last example. Woohoo! Do a little dance. Get down tonight. Right. Okay. Let's wrap this up. Let me see. So a line passes through these points. Find the equation of a perpendicular line that passes through this point. Okay. So if we want our line to be perpendicular, that means it needs to be the negative reciprocal of the given slope. But the slope isn't given, so we need to find the given slope, right? So let's go ahead and find the slope. If we're finding slope, we're going to use the slope formula. y2 minus y1 over x2 minus x1. Again, this is our slope. Okay. Here we have our x1, y1, x2, y2. So then if we plug them in, 5 minus 6 over 4 minus a -2. Okay. Looks like it's a -1 on top. Double negative is positive, so that's a 6. So their slope is a -1/6. And I'll just call it anyway. So our desired slope is going to be, the negative reciprocal is going to be 6 because we want perpendicular. We also it's going to pass through the point 4, 5. So then if we do y equals mx plus b, our slope is 6. When x is 4, we're solving for b, and the given y is 5. I'll continue working over here. So then ultimately b equals, what is that? 24, -19. Okay. So then our function should take on the form 6x minus 19. Okay. And notice when x is 4, 24 minus 19 is what, 5, right? That's a desired result. I'm just going to move this just a little bit. Okay. So we got 6x minus 19. 6x minus 19. You can see it there. Okay. All right, ladies and gentlemen, we did it. My device survived, in low power mode. We started at 20%. We are currently at, take a moment. What percent do you think we're at right now? All right. Right. We're at 9%. It held strong. Like, if for whatever reason, once it hit, as soon as I said that, it dropped to 8%. It held for a long time at 10%, then it dropped to 9%, and then just now it dropped to 8%. But we're done now. So, all right, ladies and gentlemen. So that was our, we needed to we shift the order a little bit. I'm probably going to do a bonus lecture on section 3.3 just for completeness. I don't think you're necessarily responsible for that directly. I think your next part for next week shows up at section 3.4, right? So with that, we're going to go ahead and end the session here. And from one beautiful mind to another, have a wonderful day. Take care. Until next time, peace.